Hi, I'm Alistair and I make playful technology experiences. And in this video, I'd like to show you some interesting things you can do using one of these. I've always referred to this as a plasma ball, but I've also seen them called plasma globes, lightning balls. I'm sure you've probably seen them before. And you can bring your hand up against them, and when you do so, you get this lovely electrical arc coming to your fingertips. And I've always thought that this would be a really great prop to use in an escape room. So you can style them in different ways. I've got one down here. This is a bit more kind of fantasy styled. This could be sort of a dragon orb or something being held in the mouth of some creature or other. This one here, this is a bit more sort of science fiction-y. And in fact, a plasma ball of a very, very similar design to this was used in an episode of Doctor Who, where it was meant to be the time controller used by Renegade Dalek.
Time controller activated. Calculating coordinates.
You will come with us!
Pretty dramatic stuff. But if we want to use a plasma globe like this in an escape room, we don't simply want it to look pretty. We want to be able to detect when a hand has been placed on it. So we can use that to trigger an effect, or as the input to a puzzle or something like that. And to do that, we're going to use another component. So this is a INA219. You see it says on it it's a current sensor. Now, in fact, this is a little component that will detect both the voltage across a circuit and also the current passing through it. And you can read those values using an I2C connection to a Raspberry Pi or an Arduino or something like that. Now, what's interesting about these globes is that when they're at rest like this, so when nothing is touching them, they will draw a certain amount of current. When somebody places a finger on them like that, that current increases, so the power being drawn by the globe increases as well. So I've got one of these sensors plugged into the power supply for this globe at the moment. Now if I just turn my Arduino monitor on, so you can see now this is showing you the power across the bus, which is currently supplying this globe. Now as I bring my hand and place it on it, what you can see is that that power has increased. Remove my hand again and it goes back to the base reading again. So what we can see there is that you can define two different states based on the reading of the power being used across the power supply that's being used by the globe here. And on the basis of that we can detect whether a hand is being placed on it or not. So if we can do that, we can use these as something like a button input to a puzzle. And that's what gave me the idea for this project. And here it is. So as you can see, I've got two plasma balls here, and these are sold as USB powered plasma balls. So they run on 5 volts, and I've got a 5 volt DC supply coming in the top of the board here, which is powering them both. Now, into that power line to each ball, I've inserted an INA219 sensor. And those are being monitored by the Arduino down here. So the Arduino is running a sketch, which when it first fires up, calibrates itself to the base readings that you get from each of those globes. And then it's constantly monitoring those levels of each one separately. When both sensor readings exceed a certain threshold above the base power reading they were, that's what solves the puzzle. And when that happens, what the Arduino does is it triggers this relay module down here. This supplies power to the linear actuator, which then either extends or contracts. And I've placed this comedy oversized key on the end, which can symbolise some kind of prop or item or clue, which the players will then receive in order to progress through the game. So let me show you some action. And if I kind of reach across, you can't really see what's going on. So I'm going to stand behind it, reach around and get a good handful of these orbs. And this ends up looking a lot ruder than I thought it was going to. But when I place my hands on them both, you'll see that the linear actuator extends and the key comes up. If I let go of them both, that goes down again. If I only hold one, nothing happens. I do need to be constantly holding both. And you need to hold that down. It's about 10 seconds with this actuator to extend to get to the top. You can get ones that have different speeds and different extensions and things like that. And then when it's got to the top, the idea is the players will be able to retrieve the key, then they can let go and move on to the next puzzle. Now, one of the reasons I chose to use a linear actuator in this puzzle, so most of my projects in the past for escape rooms, I've had a maglock in them. So the idea is you solve the puzzle, you do whatever input is required, and when you do that, a maglock releases, opening up a box or a drawer, some other area. Now for this one, I've used an actuator, and there's two reasons for that. One is just to add a bit of variety, and to demonstrate the fact that not every escape room tech puzzle has to end with a maglock being released. But the other one is because I wanted to kind of draw attention to the fact that the output of a puzzle needs to be matched to the input. In this case, the input is holding these two plasma balls continuously for a period of time. It's an input that you actually need two players to do. And in a room, you'd probably imagine these globes being separated by some distance. So you'd actually have to coordinate the actions of two or maybe more players. You can have up to 16 of these INA 219 sensors all being monitored by the same Arduino. That's a lot of players to have, but maybe you could have 4 balls, let's say. 4 players have to touch them simultaneously and hold them down. And because that's a continuous input, I think it's nice to have the output then being a fairly slow moving thing that they have to wait for the reveal, for this key to be revealed. And then possibly, one of them has to rush to get it so that, as soon as the first player lets go and runs to get the key, it starts to go down again. So you have to get there quickly. In my other puzzles, because the input has been more instantaneous, so it's flicking a switch or pressing a button, that's a very instantaneous action. So it makes more sense for the output to be an instantaneous response as well. So I just wanted to use this for those two reasons. First of all, for a bit of variety, and secondly, just to make you think about how the different sort of outputs you might want to use might need to be matched to the inputs. A couple of other things to mention as well. I'm using a 2-channel relay here. So again, with a maglock, I've normally only been using a 1-channel relay because the maglock is either powered or it's not powered. That's what makes it locked or unlocked. With my actuator here, I need it to actually have, potentially 3 states. I need it to be extending, in which case you need to supply a DC current in one direction. Or you want it to be contracting, in which case you want the DC current to be reversed. You want the polarity to be supplied the other way around. Or you just want it to not move at all, in which case you don't want any current to flow. So for that, I've got a 2-channel relay here. And that's going to reverse the polarity of a 12-volt DC supply to the actuator to be able to control it to go up or down. So that's why I'm using a 2-channel relay rather than a 1-channel relay. The Arduino, I'm using an Uno this time. You can use a Nano or anything else. There's nothing special about that device at all. And the only other things of note, I suppose, to mention are actually just the way I've connected up the top here. It looks a little bit messy here. I'll show you the wiring diagram in a moment. These are something called WAGO connectors, or WAGO connectors perhaps. And you often find when you're doing projects with an Arduino or something like that, there are certain pins that you need to plug more than one device into. So ground and 5 volts are obvious examples, I suppose. If you have a number of sensors that are all running at 5 volts and they all need to be wired into the 5 volt and the ground pin on the Arduino, you kind of run out of pins quite quickly. In this example, both of my sensors up here are running off the same I2C connector. So they both need to be wired into the A4 and A5 pins on the Arduino. And these little blocks here are a really useful way of doing this. So I'll put a link in the product description, but basically they're just little clip connectors, and you can get modules that have different number of connectors available, so you can connect anything from 2 wires up to about 8 wires connectors. And you kind of flip these levers up, push a wire in, flip it down, and then that creates like a mini bus between any number of cables that you need to join together that need to go to the same pin. So rather than trying to sort of splice them together or do some complicated wiring, if you just want to have a push connector that just has some bare wires pushed into it to create a quick circuit, these are really handy little things to have. So I just wanted to talk about those. Let me show you how this is wired using a diagram in Fritzing to lay it out a bit clearer. So let's start at the top, and I've got my 2 plasma balls here. So like I said, I'm using USB plasma balls that run off 5 volts. So I've got my 5 volt DC input that powers each one. The INA219 sensor itself can be used with power supplies up to 36 volts and I think 2 amp maximum. So if you've got a 12 volt plasma ball instead, that's fine. You just have a 12 volt supply coming in here. So it's just the regular power supply that goes with the plasma ball you're using. And then what you'll see is that the positive line here, so the positive 5 volts, I've got going into the V-in plus pin on the INA219, and then the V-in minus I've got going to the plasma ball itself. So I've inserted the sensor into the positive line, and it does matter which way round. So you want the power supply coming into the plus side, and then you want the load, which is the ball itself, connected to the minus side there. And same again on this side, so the 2 sides just mirror each other basically. And then the negative line from the power supply, well, that is connected along with the ground lines from the sensor here as well to the ground of the Arduino. So we've got a common ground shared between all the devices, and that's going to be necessary to be able to make that reading of the voltage and the current across the circuit. So that's how I've got the balls wired in at the top. Then if we take a look at the sensors themselves, so like I say, these use an I2C connection or an integrated circuit board connection, and that requires 2 wires. So it has a data connection and a clock connection. The data connection, that's normally called SDA, and the clock is SCL. And those need to be wired to pins A4 and A5 on the Arduino. So those pins are reserved for use by I2C. You can't modify them because those pins are wired to the particular hardware on the Arduino that's going to be used to control I2C. So SDA, the data line, that goes to A4, and that goes to both sensors here. So we've got this split here. This is where I was using those Wago connectors on the board to create that join. And SCL, which is the clock line, that goes to A5. And they also need positive 5 volts and ground as well. So the red and the black line there are going to 5 volt and ground here. So that's the wiring on the Arduino side of the sensor board. Now, the way that I2C works, so we just have these 2 lines here. So in order to know, in order for the devices on the I2C network to be able to talk to each other, every device needs to have a unique address, which is normally defined on the hardware somewhere. Sometimes it's set using a little jumper, which you use to connect pins. And on these devices here, it is some solder pads, which are marked A0 and A1. So when the board comes supplied, neither of those pads are connected, and the address of the device when it's just like that in hex is 40, which is the decimal number 64. If you solder the A0 connector, so if you make a little blob of solder that touches those 2 metal plates there, that increases the address by 1. So you've now got an address of 0x41. If you connect the A1 pad across the top, that gives you an address of 0x44. And if you solder them both, you get a 0x45. Now, those are the 4 easy addresses. You can actually assign up to 16 addresses, in which case you need to make a connection between one of those pads and either the SCL or the SDA line as well. But I'm only using 2. So what I've got here is the one on the right hand side. You can see I've just shown a little connection across A1 here, and this one I've left empty. So the 2 addresses I'm going to be using in my code are 0x40 and 0x44. Okay, like I say, here's the Arduino. The Arduino has nothing special about it at all particularly. I've got a USB connection going in here because I'm using the serial monitor to read the values, but you can power it from any 5-volt supply, or you can use the barrel input to power that from up to 12-volt supply. Now I've got my relay module down the bottom here, so let me explain a little bit how this works, because this might seem a bit complicated if you've not seen this before. So a 2-channel relay module has 5-volt supply and a ground line, just like normal, and it has 2 control lines here, IN1 and IN2, and for that I'm using pins A0 and A1. So although they can be used as analog input pins, I'm using them as digital output pins. They just happen to be on the side of the board that was closest to the analog pins, so that's why I'm using those boards there. And just like a single channel relay, these can be individually turned on or off. So the common connection in the middle can be split between either the normally closed or the normally open input, depending on whether the IN1 or the IN2 signals are high or low. Okay, so there's nothing uncommon there. So how can we use this to make the linear actuator rise up or contract? Well, so I've got a 12-volt supply here. I'm assuming that your actuator is running at 12 volts. Most of the ones I've seen certainly do. And I just want to show you how that's wired. So I've got the positive line from the 12-volt supply is going to the normally open connector on the top relay block here, and I've also got that connected to the normally open connector on the second relay. So these are always at 12 volts, both of them. Okay. Then I've got the negative line from the DC supply here. That is going to the normally closed connector of the bottom relay block, and that in turn is connected to the normally closed connector of the top one as well. Okay, so we've got the 2 normally closed connectors. They're connected to the negative line, and the 2 normally open connectors are connected to the positive line. Now the 2 wires which are going to my linear actuator, they are connected to the common terminals of the 2 relays. So imagine what happens, the state of this relay when the power is off, for example, or when the sketch first starts up, and the relays are both in their normally closed positions. That's what normally closed means. It's the state that the relay is going to be in when it's at rest. So when they're both normally closed, we've got the connection here, common is connected to normally closed, which is negative. And this one here is also connected to normally closed. So they're both at the same potential. They're both connected to the same wire. So no current is going to flow and the actuator is not going to move. Now imagine that this relay at the bottom, we're going to leave that one as it is, but we're going to send a signal down the input line here to activate this relay at the top. So this relay is now going to go from the normally closed position to the normally open position. And when it does that, this line here, this grey line, this is now connected to this terminal here, which has got positively connected to it. This one at the bottom, this is still connected to the normally closed connector. So we've now got a 12-volt potential difference between the two wires that are connected here. And that's going to make the actuator extend, because current is going to flow, there's a 12-volt difference, the actuator is going to go up. Then, if we reverse that situation, so now what we'll do, we'll let the top relay block go back to being its normally closed position again. Well, that's back to the negative line, so when they're both on the negative line, nothing happens. And instead, we'll open the bottom relay. When that happens, this one here connects to the normally open position. So we now have this line to the actuator connected to positive 12 volts, and this one is connected to the negative line instead. So what we've done is we've reversed the polarity of the connection by flicking these two common pins in the middle between the top and the bottom. We can reverse which direction this DC supply here is being applied to the actuator. So when they're both closed, they're both at the negative line, nothing happens. When they're both open, they're both at the positive voltage, and again nothing happens because you need a voltage difference to do something with the actuator. But when one is open and the other one is closed, that's going to make the actuator extend. Or if we reverse it and the first one is closed and the other one is open, that's going to make the actuator contract instead. So that's kind of, it's a little bit complicated, but that's actually a really useful way to understand how you can use relays, not just to turn something on or off, but to actually reverse the polarity of a DC supply to a component. I mean, you could equally use that for a DC motor, let's say, if you wanted to make it spin in a different direction. You can do so using a two-channel relay in exactly the same method that we've got there. So remember, to do so, it's just a matter of these two input lines here. When they have the opposite state of each other, when one is high and one is low, something's going to happen. If they're both high or both low, nothing's going to happen. And I think that is it for the wiring. So here's the sketch that's running on the Arduino, and if you've followed any of my previous projects, you'll know that I use a fairly constant format and structure for my code, and this project basically follows the same format. So I always start off with some definitions, and I've got a single define here that is called debug. Now, what that means is that while this line is included at the top of the code, further down the code I can include sections like this bit here, which are only going to be included and only executed in the code if that is true. So while this line at the top of the code is there or not. If I comment this out by putting two strokes like that, any sections of code that have been enclosed in these little if, def and end if statements are no longer going to be included or executed. But I haven't had to comment them out and I haven't had to delete them from the code, so they're still there. It's just a convenient way to have conditional sections of code that you can easily turn on or off. Now, in this project particularly, what you're going to need when you first run it, you're going to need to calibrate the code for the power levels that you get for your particular plasma balls. And that's going to be something which varies depending on the exact devices you use. So it's not something I can hard code into the code. So included in the sections of code that are conditional on that debug here, you'll see I've got some sections here that actually write out to the serial connection what the average sensor reading is, and I've also got this setup here. I've got what the sensors were initialized at. So all this extra information is only going to be included while this line is true. So you want to leave that there while you first set the project up, while you test it, while you make sure it's running, and then when you're happy that it's okay and you're ready to move into a live production environment, you can simply comment that line out, and all those extra sections of code later on will no longer be included in your compiled code, will no longer be executed. And they're not taking up memory, they're not taking up processing time or anything like that, but you haven't actually had to modify your source code at all other than just that single line there. So that's why I do that. Then we move on to the include section. So an include is an external library of code that includes some extra functionality not defined in this sketch file itself. So I've got 3 includes. The first one is the wire library. That comes with Arduino itself and is used anytime you want to use some kind of device that uses an I2C connection. Then I've got a library of specific functionality just for that INA219 sensor, and I'm using this library here that I got from GitHub. So that's going to contain the functions that retrieve the power and the current and the voltage that's being read across that circuit connected to the plasma ball. And then I'm including one more set of code here. So remember right at the beginning of this video, and I showed the serial plotter graph of the bus readings when I was touching the plasma ball and when I released it. And you'll notice that the line was quite sort of jittery. It's quite noisy signal. So rather than relying on the raw sensor values, what I'm actually going to do is keep a running average of the sensor values, and that's going to help smooth that signal out. So I'm going to record the last however many readings, add them up and divide to get an average reading. And this library here is going to contain the functions that's going to do that for us. Then we move on to the constant section. So these are values which are not going to change throughout the duration of the code. And I've defined the number of sensors we're using as a variable here. So that's to make it easier for you if you want to use more sensors, if you want to have 3 or 4 or 5, or like I say, anywhere up to 16 plasma balls in your circuit. That's the maximum number of INA219 devices you can have, because they all need to have those unique addresses on the I2 system. So I've defined that as a variable. I'm just using 2 for this example. And we also need to define the pins that the relay modules are connected to. So we've got 2 pins, and they are A0 and A1. Like I say, they're analog pins just because they were the ones that are on the correct side of the board, but you can use any spare GPIO pins there. And they're going to the signal input 1 and 2 on your relay module. So then we go to the global section, and we're going to define an array of sensors. That array is going to have num sensors elements in it. So in my case, I've got 2 sensors, but if you wanted to define more sensors, you'd simply add more elements onto the end of this array here. And each one includes the unique address that's been set for it. So I've got one INA219 sensor that's just out of the box, and so that's the default I2C address. And I've got one where I've bridged that A1 jumper, so that has got an address of 44 in hex there. But you can add more elements on there. Here we've got another array. This is an array of floating point values, and this is what's going to record the base reading for each of our sensors. So when the code first fires up, we'll establish a base reading that it just records when it's not being touched, and we'll record that in an array here. And then we'll also have an array of the running average values. So once again, that's going to have number of sensors elements in it, because we want to record one running average for each plasma ball, for each sensor. And I'm using 5 as a value here. So this is going to be how many readings we're going to keep track of for each sensor. So I'm going to record the last 5 readings for each sensor, and I'm going to average those out, and I'm going to take that as the sensor reading. If you define a higher value here, so let's say you include this to 20, that will average out the last 20 readings. Now that's going to give you a smoother signal, so it's going to get rid of more noise, but it's also going to make it a bit more sluggish to respond to when a touch is actually felt, because you're going to have to wait for that average to rise up, which is going to take longer. If you set it to a lower value, you'll get a quicker response, but there's more risk of you getting sort of that noisy signal. So 5, that was kind of a slightly arbitrary number I chose, but it seems to work for me. Now we move on to the tolerance value. So this is the value that's going to determine how sensitive your system is in detecting the touches. Because what we're going to do, we're going to take this average reading. So we've smoothed out the noise already. Then we're going to take the average reading for each sensor, and we're going to compare it to the base reading that that sensor gave us when we weren't touching it. And if that deviates by more than this amount here, that's what we're going to record to say that a touch has been felt. Now, again, I set this value somewhat based on trial and error. So this is where you're going to want to have this debug line here. So when you run the code the first time with this debug attached here, it's going to print out the values that were set for the base reading. It's also going to print out the value that is recorded from the average reading for each sensor. And what you'll need to do is sort of touch your hand on and off the globes a few times and see how much those values change to determine what you want to use as an acceptable tolerance. So this is a totally set empirically there. There's no sort of right answer to that. That's going to depend on your system. But this is what I determined by just looking at that serial monitor output, touching my hand on and off and seeing by how much those values jumped. So now we get into the setup function. So this is what's called when the code first starts running, and we'll just chuck a bit of information out to the serial monitor link to say where the code is up to. This is useful to include if your code ever hangs or something like that. It's useful to know what the last function it was trying to do was. We'll loop over each sensor, and this is where we're going to start everything up. So we want to clear out the average readings. We want to make sure that the average at the start has got all 0 values in it. And we're also going to call the begin function from that INA219 library on each sensor. Now, the sensors can be configured to operate with different sort of ranges of values. The default in this library is for to read a voltage between 0 and 32 volts and a current between 0 and 2 amps. Now, I'm not actually using that whole range of value at all. I'm only using up to 5 volts, and I think mine goes up to about half an amp here. So I could increase the precision of my readings by reducing those values. And if you actually go and look in the INA219 library here that I'm including, if you take a look at the source code, you'll see comments there that describe how you can supply alternative configurations that will increase the precision reading here. But I found I didn't need to. This works fine for me. So I'm just calling begin with the default values there. But if you wanted to, you can call a calibration function here that changes what that range of values are that gets read. So having started everything up, what we're now going to do is take that base reading for each sensor. So that's what this section of code here does. So we're going to loop over all of the sensors, and then what we're going to do is we're going to, on each sensor, we're going to take 5 readings. So for each sensor 5 times, we're going to sense what the bus power is that's being used by the plasma ball. So at the moment, remember, we don't want to touch it at all. This is just taking a base reading. In fact, we're going to take 5 base readings for each sensor, take what the bus power being reported by the sensor is, and we're going to add that value onto our array of average readings for that sensor. So the J value here, this is what our counter is. So we're going to say for the first sensor, we'll take whatever the bus power is being recorded, and we'll add that onto the average readings array for that sensor. And then we'll do that for every sensor. Once we've done that, so we've filled our average readings array, what we'll then do is we'll take the average that we got from those 5 readings, and we'll assign that to the base reading. So now we've got a base reading recorded for every sensor, which has been calculated from the average of 5 readings taken at the start, and we just put a little delay in between each reading. That's going to also help just eliminate any noise that we might encounter along the way. So we're going to take 5 readings a short distance apart from each other, get the average of those readings and assign it to our base reading. And once again, while we're debugging, we'll actually output what that value is to the serial monitor. That's going to help us check that the code is functioning the way we expect it to. We'll then initialize the relay pins as outputs, and we'll initially send a low signal to them. So you can get what's called active low and active high relays, and what that means is that depending on whether they receive a high signal or a low signal, we'll change them from normally closed to normally open. If you find when you're running this code that you have the linear actuator extend when you intended it to contract and the other way around, what you might find is that you've got a different sort of relay, so you might need to swap your highs and lows around in the code. But that's an easy change to make. Then we got to the end of the setup function, so we'll just again just record where we're up to in the code to the serial monitor, and then we'll have a bit of a delay before we move on to the main program loop. So this function here, this is the function we're going to call to test to see whether all of our plasma balls are being touched simultaneously, because that is what we're using to change the state of the puzzle and make the actuator start rising. So this is a little bit complicated if you haven't seen a structure like this before, but another way of saying, so when all the sensors have been touched, what we're saying is that the average reading we get from the running average array for that sensor has exceeded the base reading for that sensor by more than the tolerance allowed, and that is true for every sensor. That's how we know that they've all been touched, is that the average reading for every sensor exceeds its base reading by more than the tolerance. But you can also express that the other way round. So we're saying, well, hang on, if any sensor is within the tolerance of its base reading, that means that it hasn't been touched. And if any sensor hasn't been touched, then we know that all the sensors cannot be being touched at the moment, because we found at least one that isn't. So it's kind of expressing the same condition, but the other way around. Rather than testing whether they all have exceeded their tolerance, we're testing whether any of them haven't exceeded their tolerance. So, and that's what this section here is saying. So we'll loop over every sensor. We'll get the average of readings that's in the running average for this sensor. We'll compare that to the base reading for this sensor. And if it hasn't deviated by very much, if it's still within the tolerance, then we know that not all the balls can be being touched. We'll return false from this function, and then we don't even need to test any other of the balls, because we found at least one that hasn't deviated. If we complete this section here for all of the sensors, and we haven't found any of them that are within tolerance, that means that, well, that means they're all being touched. So then we can return true, which is this section here. So this condition here might seem like it's kind of inside out, but this is quite a common way to express conditions like this in coding. Rather than testing whether all of something is true, you can test whether any of it is not true. It's the same thing, just expressed another way around. So then we have our two functions which control the linear actuator, make it extend and contract. And remember that to do that, we need to set the relay pins in opposite directions from each other. So we set one high and the other one low, or we set it the other way around, one high and one low. That will reverse the polarity of that DC voltage that's being applied across the pins to the actuator, and it will make it extend or contract. If they're both set low or they're both set high, then nothing's going to happen because there's no potential difference across the pins of the actuator. And then we go on to our main program loop. So this is what runs over and over again while the program is running. We're going to loop over all our sensors. We're going to take a reading of what the current bus power is recorded on this sensor, and we're going to add that to our array of running averages for that sensor. And then once again, if we're debugging, remember we're just going to actually put that value out to the monitor so we can see whether we're getting a sensible value or not. And we'll put the print line here. This puts a new line in after the recordings, and that means that serial plotter function will plot a nice graph for you because it will tell which readings we're on which iteration of the loop. That's all that's doing. And then we will check that function that we looked at earlier to see whether, okay, having added the latest values into the running array, let's take the averages that we have at the moment and decide whether they're all outside of their tolerance or not. If so, we'll extend the actuator, and if they're not, we'll let it contract again. And finally, there's no real need to run this code, as quickly as possible over and over and over. We're not polling a device that has a very high sensitivity, so I've just put a slight delay in there of 100 milliseconds. So this is going to run no faster than 10 times a second, which is perfectly adequately fast enough to get a decent response when someone touches it. And that's it. So I hope that's given you some ideas as to how you can use these cool little props as inputs for an escape room puzzle. And you can dress them up in different ways to fit different themes. So obviously they look a bit science fiction-y normally, but you can also get more of a fantasy feel to them, dressing them up in a prop like this. I'll be honest, they're not going to fit into every single escape room theme. But even if they don't fit with the setting of your escape room, I'm hoping there might be other parts of this puzzle that you can take away. So the use of the linear actuator, for example, as the output mechanism is something that I've not shown before. And that might fit with a certain puzzle you've got. Remember, I'm essentially using the balls here just as momentary inputs that players need to press. So you could simply replace these with any style of button or other input, have many of them spaced around a room, and use that same principle that multiple players need to continuously hold an input for a period of time to make the actuator rise and to retrieve that key to move on to the next puzzle. You could make that basic setting apply in many, many different sorts of rooms. As always, I'll put the Arduino code download, the wiring diagram, and the links to where I got all these various bits and bobs from on my Patreon page. If you would like to, and if you feel able to support me, that would be amazing. But if you can't, that's fine. I will continue to put these videos on my YouTube channel here anyway. If you have any comments or questions, please put them below and I'll do my best to answer them. And I look forward to seeing you all next time. Thanks very much for watching.